Up to this point, we've looked at the weights and tensions you should take into account when rigging is a part of a job. Specifically, we've seen how to determine the approximate weight of a conductor on an insulator, as well as three types of tension: line tension, bisect tension, and guy tension. In addition, we've looked at how you can calculate a safety factor into your rigging requirements. During this part of the program, we'll determine weights and tensions exerted on a typical corner pole. We'll also look at how the weight exerted by a conductor changes when it is raised above its initial sag, and how that weight increase must be factored into planning. The purpose of this example is to demonstrate how the weights and tensions for a job can be determined. Although the work procedures and construction styles may be different from those at your company, the basic principles remain the same. In this example, 3 phase conductors and a neutral are to be moved from an existing pole to a replacement pole. This job is commonly known as a pole changeout, and it will require considering all of the weights and tensions we've looked at in this program. The replacement pole, which is 45 feet from the ground line to the top, has been set into position beside the existing pole, which is 40 feet from ground line to top. The heights of the poles in this example have been selected for convenient figuring. When conductors are moved to a taller pole, the weight exerted by the conductors will increase, since the lowest point of conductor sag in the adjacent spans will be altered. The extent to which the weight increases depends on how high the conductor is lifted, or, in other words, the extent to which the lowest point of conductor sag is moved towards the adjacent poles. The maximum conductor lift possible, without applying undue strain to the tie wires at the adjacent poles, occurs when the lowest point of conductor sag occurs right at the adjacent poles. When the maximum lift has occurred, the weight exerted by a conductor is approximately doubled. So, in order to find the weight exerted by a conductor when it is raised to the maximum height possible, multiply the weight of the conductor exerted on the insulator by 2. Now, before the conductors are lifted and attached to the new pole, guy wires will need to be installed on the new pole to hold against the bisect tension exerted by the conductors. With this information in mind, let's return to our example and determine the bisect tension. Then, we can determine the guy tension needed to hold against the bisect tension. In this example, the 3-phase conductors and the neutral are 4/0 ACSR. According to the chart we saw earlier, the conductor weighs 0.290 pounds per foot. The length of the spans on each side of the pole are 250 feet. And there is 48 inches, or 4 feet, of sag in each span. With this information in mind, we can calculate the approximate weight exerted by each conductor and the bisect tension. The approximate weight of a conductor on the corner pole can be determined by adding span A to span B, dividing the sum by 2, then multiplying the result by the conductor weight per foot. In this example, both spans are 250 feet long. 250 plus 250 equals 500. 500 divided by 2 is 250. So, 250 is multiplied by the conductor weight per foot, which is 0.290 pounds. This results in an answer of 72.5 pounds. So by rounding off this number, we know that each conductor is exerting a weight of approximately 73 pounds of downward force. Now remember, lifting each conductor to the maximum height permissible will double the weight exerted by each conductor to approximately 146 pounds. And since in this example there are 3 phase conductors and a neutral, we can multiply 146 by 4 to find that there is a total of 584 pounds exerted downward on the pole by all of the conductors combined. Now, because this is a corner pole, the bisect tension must also be calculated. This can be done by using the bisect tension formula. Bisect tension equals line tension divided by 100 times the length of the bisect line times 2. In order to find the bisect tension, we must first find the line tension, then the length of the bisect line. Line tension is equal to 0.290, which is the conductor's weight per foot, times 250, which is the span length, squared, divided by 8 times 4, which is the sag in feet. Working through the formula gives an answer of approximately 566 pounds. It's important to remember that in this example, that's 566 pounds per conductor. Now, to find the length of the bisect line, extend a line from the corner pole 50 feet in the direction of the conductor as if it continued in a straight line. The end of this line is called point A. Next, 50 feet is measured off in the direction of the line. The end of this measurement is called point B. The distance between points A and B is then measured. In this case, it's 17 feet. So we know that the length of the bisect line is also 17 feet. These figures can then be used in the bisect tension formula as follows. 566, which is the approximate line tension, is divided by 100, which gives an answer of 5.66. 5.66 is then multiplied by the bisect line, which is 17 feet. The answer is 96.22. 96.22 is then multiplied by 2, which gives an answer of 192.44, which will round off to 192. So there is approximately 192 pounds of bisect tension exerted by each conductor. Because there are 3 phase conductors and a neutral, the bisect tension is multiplied by 4. This results in a total bisect tension figure of 768 pounds. Now in this example, 4 permanent guy wires will be installed from the new pole to the existing anchors. Typically, more than 1 guy wire is used to counteract the total bisect tension exerted by 3 phases and a neutral. We can determine the guy tension required to offset the bisect tension by using the guy tension formula for each guy wire. As we saw earlier, this formula reads guy tension equals bisect tension divided by anchor distance times guy length. In this example, we've determined that the bisect tension exerted by each conductor is 192 pounds. In this case, there are 2 permanent anchors. One is 40 feet from the new pole, and the other is 38 feet from the pole. So now we have 2 of the values we need to fill in the formula. The last value we need is the length of each guy wire. As we saw earlier, this can be determined by making a scale drawing. For example, this line represents the height of the topmost conductor on the new pole, which in this case is 45 feet. We'll say that an inch equals 10 feet, so this line is 4.5 inches long. This line represents the distance from the base of the pole to the anchor farthest away from the pole, which is 40 feet. Using the same scale, this line is 4 inches long. Next, the distance of the line that represents the guy wire is measured. It works out to 6 inches, which by using the same scale represents 60 feet. Now we have all of the values needed to determine the guy tension required to offset the bisect tension exerted by the top conductor. Guy tension equals bisect tension, which is 192 pounds, divided by anchor distance, which is 40 feet, times the guy length, which is 60 feet. Working through the math, we can determine that the guy tension required for this guy wire is 288 pounds. So it takes approximately 288 pounds of guy tension to offset 192 pounds of bisect tension exerted on the pole at 45 feet high, when the guy is anchored 40 feet away. You should keep in mind that the guy tension on each of the guy wires used will not be the same, even though they may be attached to the same anchor. This is because the guy tension will vary depending on the height of the guy attachment and the length of the guy wire. For example, this illustration represents the new pole, the 2 anchors, and 4 guy wires between the pole and the anchors. The 4 guy wires are attached at 4-foot intervals beginning from the top of the pole. The guy wire attached to the pole at 45 feet is 60 feet long, and the guy wire attached at 41 feet is 57 feet long. Both of these guy wires are connected to the anchor located 40 feet from the base of the pole. The guy wire attached to the pole at 38 feet is 54 feet long, and the wire attached at 34 feet is 51 feet long. Both of these guy wires are connected to the anchor that's 38 feet from the base of the pole. By using each guy wire's length and its anchor distance from the pole, the guy tension required for each guy wire can be determined. We've already determined that the guy tension on the first guy wire is 288 pounds. The guy tension required for the second guy wire is 274 pounds. The guy tension required for the third guy wire is 273 pounds. And the guy tension required for the fourth guy wire is 258 pounds. Once the weights and tensions involved in a job like this have been determined, the proper equipment can be chosen, and the rigging can be planned to safely and efficiently move the conductors to the new pole. Part of this planning involves considering a safety factor. As we said earlier, the minimum safety factor generally recommended is 5. So you should rig for approximately 5 times the weight or force you need to move. In our last example, we determined that the maximum downward force that could be exerted by lifting one of the conductors was 146 pounds. In addition, we determined that the bisect tension of the same conductor was 192 pounds. So in order to establish a safety factor of 5, the rigging used to lift the conductor should have a minimum capacity of 730 pounds. And the rigging used to hold against the bisect tension of the conductor when it is moved should have a minimum capacity of 960 pounds. Well, in this part of the program, we looked at the different types of weights and tensions that can be exerted by conductors on a corner pole. Earlier in the program, we looked at each of these weights and tensions separately and how they can be determined. Specifically, we looked at a rigging safety factor, guy tension, bisect tension, and line tension. We also saw how to determine the weight of a conductor on an insulator, and we began the program by looking at the difference between static force loads and dynamic force loads. What we've looked at here should give you the base you need to plan safe and efficient rigging. Remember, your understanding of weights and tensions and the rigging required to overcome them will determine whether a job is simple or complex, safe or unsafe.